everyone, and it's my distinct honor today to introduce Professor Adam Smith. Adam is a professor of computer science at Boston University. Before that, he got an excellent start to his career at Penn State University. Before that, he did a postdoc at Weizmann, he did his PhD at MIT, and notably, he did his bachelor's at McGill, where he received the Governor General's academic medal. And you may be able to infer Adam is Canadian. So he's an example of Canadian excellence in the diaspora going on and, changing the world. To read from his website, his research interests lie in data privacy and cryptography and their connections to machine learning, statistics, information theory, and quantum computing. But let's go off the script and let me tell you what he's probably best known for is being one of the inventors of differential privacy. Differential privacy, probably essentially everyone here has it in their pocket. It's on, a lot of different things, including Apple phones, Google phones, and if we were in the United States, I would say everyone's data here has gone through, Adam's invention because differential privacy very notably was used in the 2020 US Census. Differential privacy has obviously been like a huge thing. Him and his co-authors for their work have received a number of accolades, including the Gödel Prize, the Paris Technologics Award, the TCC Test of Time. Interestingly, in 2006, when this was introduced, they were the runner-up for the Privacy Enhancing Technologies Award, which I find a little bit amusing in hindsight how much it impacted how influential it's been. Beyond introducing the definition, we've done deeply foundational and technical work in differential privacy, which is too numerous to name. It's particularly done a lot of stuff on private estimation, which has been influential in my own work and research. And just to say that he's not only a differential privacy guy, he's also received a Test of Time award at Eurocrypt for cryptographic work on fuzzy extractors. So there's a lot more that I'm not talking about. It's common in these introductions just purely talk about research, but I think that would be doing a disservice to all the amazing things Adam does. He's an amazing teacher. Lots of his lecture notes are online, and I've used them in my own learning as well as preparation of my own teaching materials. He has a course on differential privacy, which is excellent with videos, lecture notes, and everything. He's been recognized by the department multiple times for his teaching abilities. And one thing that I think is really special is that he's an amazing community builder. Over the last decade, he's organized no fewer than a dozen summer schools, workshops, and nowadays Boston is kind of known as kind of the mecca of differential privacy research. There's a huge community there, and that's in no small part thanks to Adam's leadership there. To conclude on a personal note, he's always been a very thoughtful and level-headed mentor. One of the people I turn to, when there's uncertainty or I need some guidance. So that's why it's a deep honor for me to be the one to introduce him. So thank you, Adam, for being here. And no further ado.
All right. Well, thank you very much. Thank you, Gautam, for the introduction, the warm introduction, and of course, thanks for inviting me to come. It's a pleasure to be back at Waterloo. I've come a few times over the years, and I've always enjoyed my visits here. Okay, so today I'm going to give this talk. I'll be talking for the entire time about a problem broadly known as statistical data privacy, and maybe as kind of a prototype of the problem, you might think of the problem faced by something like the United States Census or Statistics Canada when they run their decennial census. They collect a bunch of information from individuals, and they want to make that information as useful as possible, as available as possible to outside users. Those could be researchers in academia, they could be policymakers, could be companies, and the kind of information they want to make available takes lots of different forms. Everything from very simple statistical summaries like a pie chart to trained statistical models of various kinds, synthetic data, lots of different things. And really this problem, the issue that they face is to make as much of this information available as possible while providing some guarantee of confidentiality to the people whose information they are managing. And this problem really is faced by almost any organization that collects individual level information if that information is sensitive, right? And so these are This is everything from, the tech companies we know, government statistical agencies of various stripes, educational institutions like the ones we work at, hospitals and healthcare centers and people who collect and manage clinical data. There's sort of lots of different places where this comes up and where they all kind of face the same sort of basic tension between trying to get as much information out there and managing the fact that the thing that makes this information valuable is exactly what makes it very sensitive, because it paints this sort of very detailed portrait of our lives, right? And so we're managing these two conflicting goals. On one hand, we want to get as much useful work out of this data as we can, and also kind of try to provide some notion of some guarantee of privacy. And this basic tension has been the focus of a fair amount of work. It's what we mean by usefulness or utility varies from setting to setting, but it is by and large something that is pretty well understood, because usually the people who are trying to use the data know what they were trying to do with it. What we mean by privacy is sort of less obvious, and really that's going to be the focus of at least some part of this talk. Sort of what exactly do we mean? And this is it's a question that's been studied actually as far back as the 1960s in statistics and in computer science, and starting in the 80s or so. But this talk is really going to focus on a line of work that's about 15 years old now, going on 20, that looks at sort of putting this area on more rigorous foundations. And I'll try to give you, there'll be some parts of the talk that are, telling you about ideas that have been around for 15 years, and some parts of the talk that are telling you about much more recent work that I've been involved in. And so we'll sort of bounce around a little bit historically. Okay, so just sort of, quickly, I'll try to, three parts of the talk. One, I'll try to explain what is challenging about privacy and what makes this problem both practically and intellectually challenging. And I'll illustrate this with some recent work with a student of mine and some colleagues on memorization and the need for large models in machine learning. I'll talk a little bit about this concept that Gautam mentioned, differential privacy, and explain where it comes from and why. A little bit about what the sort of conceptual framework is there and why it's useful. And then I'll sort of talk a little bit about some application to a statistical problem, estimating the mean of a Gaussian distribution, very basic statistical problem which we're still seeing results coming out. We still don't know everything there is to say about it, and it's a useful problem to study because it's a kind of prototype for a lot of statistical inference and machine learning problems. Okay, so let's just start with the first one. Why is this challenging? So let's say we've got some data set that we want to get out there, and we want to, the first thing we might want to do is just to remove the stuff that's obviously identifying, names and social insurance numbers and telephone numbers and that kind of thing, and just put out what's left. Okay, and that could be a problem because it could be that the sort of identifying information like exact addresses is exactly the thing you need to study. So for example, if you're studying, if you're doing contact tracing and you're looking at how COVID spreads within a university dorm, you actually need to know exactly where people are, like not even to within 2 blocks, right? You need to know what room they're living in. But the sort of maybe the more fundamental problem from our point of view is that this doesn't work. Okay, so here's a photograph. I've grayed out the subject of the photograph, the face of the subject, but most of you fairly quickly figure out who this is. Not because you can see his face, but because there's all these other clues that you pick up on very quickly in this picture, right? There's these other things that tell you there aren't that many people who stand behind this particular podium or lectern, and there aren't, and of them, even fewer historically have had brown skin, and it's just a very small set of people very quickly. And in some sense, this is obviously a toy example, but this is sort of the real problem with this idea of identifying attributes, which is that in some sense, anything that carries information can be linked to other information sources. And what's going on is that you're connecting these little bits of information in this image to other things you know about the world, right? And this is sort of a kind of a consistent problem with attempts at sort of anonymizing or removing identifying information from data. This particular example is kind of a funny one because a group went ahead and just tried training a language, not language model, a facial recognition model on what was then the YouTube face blurring algorithm, and it actually worked pretty well. Like even though the face blurring algorithm fools humans, it didn't fool the model. Another example that I've always liked is how people took genomic sequences from which names and identifying information had been removed. And they were able to, for some part of the population, reliably guess, a sizable part of the population, reliably guess men's last names. Okay, and that's because most men inherit their last name and their Y chromosome from the same person. Right, and so those last names and Y chromosomes travel more or less unchanged through big parts of that graph. And another recent thing is, there's been a lot of discussion in the US about the census and how it anonymizes data and how it did so in 2010 and 2020, which are the two most recent decennial censuses. And one of the things people pointed out is that you could reconstruct a lot of the raw census answers from the type of outputs that were produced in 2010. And like one of the things you could, census data is sort of not considered the kind of questions people ask on a decennial census are often not considered super sensitive. They're like, roughly where you live, maybe ethnicity, age, gender, that's kind of it. But it turns out even that is sort of remarkably, you can glean remarkable facts from it. In particular, you can figure out when people change genders because you're getting snapshots over time. And so, this is sort of an example that I think has been, and there's been a lot of discussion within the US statistical agencies on how to think about these problems. And so maybe the lesson from this discussion is really that this sort of kind of notion of identifying explicit identifiers is sort of fundamentally problematic because in some sense everything is an identifier. Now, you might object that the problem with these examples is that they're very finely granular, but even if we're only releasing aggregate information, we might run into trouble, and it's because it's actually remarkably hard to pin down what aggregate should mean. Okay, and that's because even seemingly aggregate statistics taken together can encode all sorts of data. And as just a toy example, a trivial example, imagine that I tell you the average salary at a small company immediately before and after some particular person resigns. So each of those, so these are two averages. Each one individually doesn't tell me much, but I can compare those two numbers and see what changed, and I can infer, if I know how many people work at the company, I can infer the two sums, and then I can take their difference, and I learn, the salary of the person who resigned. Okay, and it turns out that this principle has come up in the literature, and there's a large literature on various kinds of attacks and things that go wrong with attempts to publish even aggregate data. There are a few different lines of work in the literature. There are things like reconstruction attacks. It started with this beautiful and seminal paper, Virat Dinur and Kobi Nissim in 2003. There are things called membership inference attacks that started from actually work in the computational genomics literature around 2008. And then there's been recently a lot of work on memorization and machine learning, which kind of falls into this broad class. And I'll talk a little bit more about that in over the next few slides. But really, the thing I want you to remember is that in sort of even at the aggregate level, you can't really release everything everyone would ever want to know about the data without basically releasing the raw data in some form. Okay, there's sort of a broad, I'm oversimplifying, of course, but This is sort of a broad principle that has come to light over the last, call it 20 years. And so we need sort of tools to navigate these trade-offs and understand how to think about them precisely. Okay, so I'm going to talk about, just to illustrate some of the challenges by some more recent work on memorization and machine learning. So, all right. So one of the empirical phenomena people have found as we've started to train larger and larger machine learning models, and as we've moved to these settings where we're training these like vastly over-parameterized models that have tons and tons and tons of degrees of freedom that can be tuned as they're trained, is that they memorize all sorts of stuff about their training data that is like not obviously useful for the problem at hand. So maybe like one of the early striking examples of this was this paper, or I say early, this is like 4 years ago, this paper by a group mostly at Google, but spread of Google and Berkeley and Northeastern and a few other places, where they looked at these large language models and observed that if you prompted the right language model in the right way, you could get it to spit out exact blocks of text from its input that were like clearly not, I mean, we're not memorizing Shakespeare's sonnets here, right? These are like just random chunks of, addresses and stuff like that. Okay, these are not things that are about learning English or any other natural language well. They're just memorization, right? And then, another recent group overlapping group of authors has looked at some of these early image generation models, the stable diffusion models, and they're looking at extracting the training images. And the top, I actually forget whether the top row are the originals and the bottom row are the reproduced ones, or vice versa, but it doesn't really matter. Sorry, somehow my slide has decided to advance automatically. All right, and so I must have like accidentally memorized some of the the training time, the practice times or some timings. All right, anyway, whatever. So what we did a couple of years ago was to try and understand whether or not this phenomenon that people were observing was just an artifact of the particular ways that we are training large models, or somehow a fundamental feature of machine learning, of learning. And those of you who've watched small kids grow up, you've probably observed the way they're like sponges, and they will just memorize all sorts of random crap until they realize that it's like not actually a useful thing to remember. But they will like for example, like my kids when they were growing up, they would like learn, they would sometimes memorize like sequences of words as like one block, and they wouldn't even realize it was multiple words, right? They would just think it's like a chunk. And so, and it just takes them a bunch of time before they understand that indeed, they don't need to remember that phrase as a single block. It's actually, some sequence of words, and they can kind of think about it that way. And so we're interested in investigating this problem from a more kind of first principles perspective. And what we found is there are natural learning problems, which I'll try to tell you about, where in some sense, to be accurate with a finite amount of data, limited amount of data, the model needs to memorize information that is ultimately irrelevant to the task at hand. And that sounds like a contradiction in terms, and I'll try to explain what I mean by that. So I just want to distinguish this a little bit from what's sometimes called memorization, but maybe is more accurately called interpolation or perfect fitting. So one of the things that, this is now, 10 years ago, people figured out that maybe it didn't, that like the classic statistical way of thinking that it's sort of better to learn a very parsimonious model for a data set than a really detailed one came from the fact that if you do learn a very detailed model, in some cases you end up overfitting to the data you have and not generalizing well. This is sort of like classic machine learning theory. And over the last 10, 15 years, people have figured out there's lots of settings where, in fact, it makes perfect sense to interpolate perfectly through the data, because this helps with for various reasons with generalization or for computational reasons. And I want to distinguish what I'm going to be talking about from that, in the sense that interpolation is about storing, essentially memorizing the labels of the data you're given, the sort of values associated to each record, whereas our work is really looking at when is it important to memorize like entire examples, so like those kind of raw features, if you will. Okay, so let me kind of state the result, and then I'll Mm-hmm. So maybe in this case, like imagine, so if you've got like an image data set where each photograph is labeled with what is a category of subject. This is a car, this is a plane, this is a European swallow, right? So the label would be the kind of tag that comes with it, and the features or the example would be the actual photograph. Does that make sense? Yeah. Right. And maybe again, for context, what people have shown is there are actually lots of even statistical problems where it makes sense to learn this kind of model, a model that is powerful enough to memorize these labels perfectly, or like in a regression context, a model that is powerful enough to perfectly predict the dependent variable in a regression problem on the data, even though that sort of contradicts the classical statistical way of thinking about things. Okay, so just to set this up, we imagine we've got some data set. It's going to consist of n examples. And we're going to imagine that these are independent examples drawn from some underlying population, which we don't know. We want to learn something about this population. And we've got some, these are reasonably rich examples, but we'll just think for simplicity, they're binary. So we've just got d bits for each row of the data set. And we're going to feed this to a learning algorithm. The learning algorithm will produce a classifier. And the classifier's goal is that given some row, a row that looks like a row of this data set, so like here's one row, given it like a fresh row sampled from the same distribution, the classifier will try to predict the label associated with that, and it will be either correct or incorrect. And so our metric for success is just what fraction of the population is the classifier correct on, just misclassification error. Okay. And so the main result is that there are natural learning problems for which at every data set X of a specific size n has a special subset of records, such that this subset of records is large, say 10% of the rows. And then I think some of my animations, there we go. Okay, so so there's like a subset of the rows, so a constant fraction, let's say 10% of the rows, such that every learning algorithm with low error memorizes most of this special set of examples. And by a little more specifically, what I mean, if I've got a learning algorithm which approaches the optimal error for the underlying problem, plus that it gets within some small additive tolerance of that optimal error, then there's this quantity which we call mutual information, standard quantity called mutual information, that we can show to be large. So let me just kind of talk through this a little bit. So what is mutual information? It's some measure of correlation between random variables. It's measured in bits of information. And it is if in this case, this is the information that the model M carries about this special subset of rows. And the thing we look at is how much information does the model carry about this set of rows even for an observer that knows the underlying population, that actually knows the learning problem, knows exactly all the details of the learning problem that this algorithm is trying to solve. Okay, so the algorithm doesn't know the population, but you're going to kind of put yourself in the shoes of someone who does. And even to such a person, this classifier conveys a lot of information about the data. And where a lot of information here is this quantity here is, this is the number of bits in this subset S. Okay, so this is sort of like all the possible, this is D times S is all the information you could possibly have about S. And what we're saying is if you get within, let's say, 1% of the optimal error, then the amount of information your model has about the data set approaches this like maximal, like approaches everything. Okay, and so what it's saying is that like there's all this information in the model about the data that is actually irrelevant to the task at hand. The task at hand is entirely kind of captured by the population.
Could you say
Yeah.
what D is?
Sorry, what's D? D, oh. Sorry, let's try something. Let's try, sorry, something happened. Yeah, no, it's fine. It's the dimension of the data. I was just sort of, it's trying to highlight on the slide, but it's the dimension of the data. So it's like the number of bits per example. Okay, so what's going on is that you're, so this is these are problems where there exists a very succinct classification rule that would correctly label essentially all the data and fresh examples. But you're in this sort of regime where you don't have quite enough information to learn that very succinct rule. And so it's actually worthwhile learning a much less succinct rule if you want to do as well as possible for this amount of data. So this optimum here is defined relative to what you could do for this class of problems with like n samples with this many. So this is sort of an n-dependent quantity. Okay, and so I'm not going to spend too much more time on this, but I just wanted to explain like the statement, and then I'll maybe I can actually talk a little bit about the kinds of problems that come up. So these are the kinds of instances, not kinds of problems where we show this phenomenon. We have consider a few different examples in the paper, but one is on a family of sort of clustering problems where my data consists of a bunch of different subpopulations, and within each subpopulation there's a single label. So your job as a learning algorithm is to identify which subpopulation an example came from. And the idea is that many of these subpopulations are going to be sparsely represented in the data set. And so for these subpopulations with only one or two examples in the data set, it's actually worthwhile remembering basically the entire example that occurred, even though if you had more examples from that subpopulation, you could sort of eventually learn which features are important and keep only a succinct summary. Sorry, my slides are advancing spontaneously. All right, so this is this also sheds some light. And so I think this example sheds some light on why we see this type of memorization. It's also shed some light on why we're training these increasingly large models. So this is an old slide. You can see I've highlighted from 2022, but it's sort of striking, not least because it's on a log scale. So it's like very convex, even on a log scale. And it shows you just how quickly the sizes of the models we're training have been increasing. And if the slide extended through 2024, there'd be another few log ticks on these axes. So there have been various attempts to understand from a theoretical point of view why such huge models are useful. Okay, and just to like there's obviously a bit of like an oversimplification, but the kind of explanations we know fall very broadly into three categories. So one is sort of expressivity. The larger the class of models is, the more functions you can represent, and thus the more phenomena you can potentially capture. Another reason is that optimization, as we add parameters to these models, it turns out the optimization problems often become easier, because as you kind of add parameters to the models, it's often the case that the optimization landscape kind of flattens out, and the local minima and maxima are a little smoother and easier to jump between. And so we tend to, there are simple algorithms like stochastic gradient descent, for example, that find these optima sooner. And then a third related explanation is that the simplicity of the optimization algorithms lead to some kind of implicit regularization that leads to sort of good performance on new examples from the same distribution. So these are the kinds of phenomena that people were trying to model and understand. And our work adds a sort of a different angle on these, a kind of different, qualitatively different type of explanation, which is that large models store information whose usefulness is not yet understood to the model. So meaning these are settings where you've got enough data to do something useful, but you don't have enough data to sort of boil that useful stuff down to a very small, succinct explanation. And this is driven in some part by these sort of the multiplicity of small subpopulations and the examples we consider. I suspect in practice, this doesn't show up in our theory, but I suspect in practice it's also driven a lot by the need to have models that can be adapted easily to new problems. So obviously, if someone is giving you a data set to look at and think about, but hasn't yet told you what problem they want you to solve with that data set, then as a kind of machine learning model, what you should do is like probably just keep as much as you can around about that data set. And that is, I think, one of the phenomena that's sort of driving this sort of expansion of the size of the models we're studying. Okay, so just sort of like concluding this part of the talk, lessons, everything's an identifier. We can't release everything everyone would want to know. And we need sort of tools to navigate this trade-off and understand, what is the cost of imposing, of storing like less information, say, about individual examples, and how do we measure and navigate that, those trade-offs. Okay, so I'll tell you about one tool that has been really useful for this, called differential privacy that Gautam mentioned in his introduction. So differential privacy is it's not an algorithm per se, or even a framework for designing algorithms. It's just a restriction on the algorithm. It's like a class of algorithms, a property the algorithm can have. It's as Gautam mentioned, there are sort of deployments at there are deployments of differentially private algorithms at a bunch of big tech companies, Apple and Google most notably, but also others. There are also a bunch of smaller startups. There was sort of somewhat fairly high-profile use of this type of framework for the public use data products from the 2020 US Census. And this conceptual framework has been a key ingredient in sort of various overhauls of government statistical disclosure limitation procedures. It's showing up in the discussion about the deprecation of third-party cookies in advertising and how you can, roughly speaking, kind of get some of the economic benefits of this information collection about how people view ads and use them, and trade that off for sort of various privacy benefits. And it's also like come up explicitly in some of the proposed legislation and regulations in the US. And to some extent in other countries, I'm less knowledgeable about that, though. Okay, so let me just explain what the definition is. So we've got, imagine we have some data set which consists of a bunch of records in some domain. We'll call the domain D. These could be numbers, could be categorical data, but it could be sort of arbitrarily complicated stuff. It could be images, tax forms, whatever. Okay, so the definition is agnostic as to the format of the data. But we're gonna whatever the data is, we're gonna think of the data set as sort of a fixed quantity, not random, at least for now. But there will be randomness in the picture, and the randomness is coming through from the algorithm we use to process the data. So we're going to imagine a randomized algorithm that takes the data set as input and some additional random bits and produces a distribution over outputs. And this randomness could come from adding noise. It could come from various kinds of subsampling or more complicated things. And the essence of the definition is a thought experiment. We're going to imagine what would happen if we changed one person's data, or maybe added or removed one person from the data set. And we're going to ask how the probability distribution on outcomes changes as we change the data set. So we're going to sort of consider, we've got the blue world and the green world, and in the green world, one person's data have changed. And so these induce sort of two different distributions on the space of outputs. For simplicity, imagine the real line. And what we want is that this sort of blue curve and the green curve be close. And the reason that sort of we're going to look at that is that it's going to allow us to say that for any set of outcomes, let's say those where I get denied health insurance, these outcomes have approximately the same probability in both the blue and the green world. Okay, so it's not that I might get denied health insurance either way, but that fact won't be due to my presence in the data, the fact that my data were used by the algorithm. Okay, so that's the sort of, in broad strokes, the sort of conceptual framework. To make it a little more technical, we'll say that two data sets are neighbors if they differ in one person's data, one record. Okay, and so what we want is that neighboring data sets induce close distributions on outputs. And specifically, we'll say that we're going to sort of quantify this. We're going to say an algorithm is epsilon differentially private, where epsilon is some parameter we get to choose. If for all neighboring data sets x and x prime, and for all possible sets of outputs or measurable sets of outputs, events in the probability space, the probability of seeing this output with data set x is very close to the probability of seeing this data set seeing this output when the data set, one of these outputs when the data set is x prime on a multiplicative scale. Okay, so for convenience, we say it's like, bounded by e to the epsilon or e to the minus epsilon on the downside. But, you can think of e to the epsilon as basically 1 plus epsilon. Okay, so it's sort of telling you a multiplicative change. There's a small multiplicative change in the probability of any output. And so we should think of this epsilon number as sort of some measure of how much is leaked about the presence or absence of one person's data. And so this is a knob we get to turn. And for technical reasons, it's often convenient to also give yourself a little bit of additive slack in this definition. And I will sweep this under the rug for the rest of the talk, but it is there. And if you want to know more, you can ask me or Gautam for the sort of gory details. But I won't sort of get into the distinction of why, when it's important to have or not have this additive slack. Okay, so this is sort of the broad framework. So we've got this sort of number that allows us to control how much the distribution on outputs changes in response to changing one person's data. And this this framework has a bunch of benefits in like practical kind of features. For example, well, you've got this knob you can turn, so it gives you sort of a natural way to navigate trade-offs. It also satisfies some nice composition properties that allow you to analyze how the system behaves if it how like a complicated algorithm with many pieces behaves by analyzing each of the pieces individually and somehow combining those. I won't get into that, but that turns out to be useful. But maybe it's nice to have like just even a simple example in mind. So the simple example that we'll start with is just adding additive noise. Okay, so imagine we've got some summary we want to release about our data set. It's some function that returns a vector. And as a simple example, imagine just the one-dimensional version is that I've got like my data set consists of 1 bit for every person, which is whether or not they're diabetic. And I I want to release the proportion of diabetics in the data set. Really, maybe the most simple summary I can imagine. And so the strategy I want to consider is taking this function, adding noise to the value of the function, and releasing this noisy value. Right? And the question is, how much noise is needed? So it turns out one way to get a handle on this is to look at, well, how sensitive is this function to changes in its inputs? And specifically, we'll define the global sensitivity of the function to be the largest change in the function value I can get by changing one person's data. Okay, so this is if you're from a sort of math background, this is an Lipschitz constant, if that's helpful. Okay, so what we're asking is like, how much can I, in some sense, I've got this kind of geometric picture where I want to know how much does this sort of calculation of these summary statistics, how much does it conflate or distinguish points that are data sets that are nearby in data set space, meaning they're differential only. Like how much are the distances in data set space amplified or squished by this function? Okay, so for example, for the proportion of diabetics, the global sensitivity is just 1/n, because if I change one person's data, the proportion of diabetics goes either up or down by 1. By the number of diabetics goes up or down by 1, and so the proportion changes by 1/n. Okay, so how does this connect to noise addition? Well, it turns out that if we add noise whose standard deviation is scaled to this global sensitivity, then we can satisfy this definition of privacy. And roughly speaking, I could imagine adding, let's say, normally distributed noise, like Gaussian noise. And there, as long as my standard deviation per entry is sort of scaled to the global sensitivity divided by epsilon, then the resulting process is epsilon differentially private. Okay, I'm cheating. I've got quotes on the theorem because I said I'm cheating on this additive slack parameter, but morally this is a true statement. And so what should you notice about this is that when the more sensitive your function is to changes in its inputs, the more noise you add to somehow to hide those changes, which makes sense. And then the smaller, the less leakage I want, the more noise I have to add, which is, I think, intuitive. So just quick sort of proof by picture, what's going on? If I consider changing one person's data in the data set, I'm basically translating this distribution on outputs by a little bit. And this global sensitivity tells me, how far apart the means of these two distributions can be, and then we just add enough noise to essentially swamp that change in the mean of the distribution, so those curves are comparable. Okay, so let's just see an example of where this comes up in maybe somewhat higher dimensional version of this, and why it already gives us something pretty interesting. Okay, so this is the same so-called theorem from the previous slide. So let's consider a higher dimensional version of the proportion, which is just a mean estimation problem. So imagine I've got a bunch of data points in some high dimensional space. These are points that live in these are d-dimensional vectors, and I want to compute their empirical mean. So this is just like the average of these vectors. So let's suppose for a minute that I knew that all the data records I know some bound on how big those vectors can be. Let's say they have Euclidean norm at most 1. Let's say because that's just a feature of the data schema that each coordinate can only be so big. Incomes are between or maybe capped at some reasonable number. Ages are capped at call it 120, whatever it is. Okay, suppose I know this, then what then can I say about the sensitivity of this mean? Well, I know that if I add or if I change one person's data in the data set, then I can sort of, I could maybe move some point from where it is to some other place, and that would sort of drag the mean a little bit in the direction of the new location. But it can move by a distance of at most 1/n, because it's I'm changing one of the endpoints in the data set. And so that means that I can, using this thing on the previous slide, I can add noise that's on the order of 1 over epsilon n per entry in the vector. And so the sort of total distance of my noisy empirical mean from the original is going to look something like square root of d over epsilon n. Okay, so why is this kind of what do you notice that's what can we notice that's interesting about this? First of all, as long as my data set size is big enough, then this error is still going to be modest. It goes down. The error goes up as I make the privacy parameter smaller. That makes sense. And it also goes up with the dimension, which is maybe like the more disturbing thing about this. We'd ideally like not to pay too high a cost for releasing higher dimensional summaries. But it turns out that this is actually as good as you can get. Okay. And that's because in parallel to this theory of sort of developing private algorithms, people have been working on, a theory of what kinds of attacks are possible, as I mentioned earlier. And one line of this work shows that any mechanism for this problem that releases values much more releases a vector whose distance to the mean is much closer than square root of d over n, you can actually attack such an algorithm. You can use it to extract individual level information. And specifically, what you can do is, it's called membership inference, is like given some of the coordinates of one person's vector, I can test if that person is in the data set or not. Okay. And so we get this situation where the sort of we kind of know how to think and analyze algorithms that get error like a little worse than this bound, a little larger than this bound, and anything that's significantly improved on that algorithm, on those algorithms, would actually be subject to an actual like actionable attack. And these membership inference attacks, I should mention, have also become like a really a sort of a staple of how people think about privacy as they're training these larger machine learning models. There are sort of various, there's now a large literature on making these work empirically in practice in machine learning, and they're used for auditing models at companies like Google and elsewhere. Okay, so so this is just an example of some stuff we can do. Maybe it's useful to sort of think about what are the benefits of using this framework? What do we get out of thinking about things this way? And so I just want to talk a little bit about how we might like interpret the guarantees, these sort of guarantees that we're getting from differentially private algorithms. So here's the kind of interpretation we might like to take. And if you've taken a cryptography class, this will sound really familiar. We might want to say something like this. Okay, if you are an outside observer and I am a person in the data set, we might like to say that your beliefs about me are approximately the same after you see the output as they were before seeing the output. And the problem with this interpretation is that it's actually impossible to achieve. And it's impossible to achieve because we're actually trying to do something useful here. Okay. And to see why this is, maybe this is like proof by story. Suppose you know that I smoke. Okay, like suppose you saw me outside on the sidewalk smoking a cigarette, right? So you have the side information about me. And then imagine it's sort of like episode 1 of Mad Men, 1960s, and we have not yet figured out that smoking and cancer are strongly correlated. And there's this clinical study that comes out that demonstrates a strong connection, right? Now, the question is, have you learned something about me? And the answer is, hell yeah, right? Like in particular, you have learned that I'm a terrible health insurance risk, right? But you've learned, and maybe like not a great, person to date, right? Like, because I'm likely to be, I'm much more likely than the baseline to get lung cancer in the future or emphysema or whatever. So you've definitely learned some actionable information about me, but not because my data were included in that study. What you've learned, the thing is the study taught you this like fact about human biology, not about me, right? And so what differential privacy gives us is sort of that in some sense, those are the only kinds of inferences that can be made. That no matter what you know ahead of time, you learn almost, where almost is up to epsilon, the same things about me, whether or not my data were used in the computation. Okay, so we can also argue that that differentially private algorithms sort of provably resist the attacks I mentioned earlier. And that's fine, but this is sort of I think the most satisfying intuitive understanding of like way to think about what's going on. And one can formalize this type of statement in a sort of a Bayesian framework with posterior probabilities and such. But I think that the English language version captures the essence pretty well. Okay, so at this point, there's like lots of work on differentially private algorithms, on developing algorithmic tools, basic theoretical results on learning and optimization and statistics. There are lots of variations on the definitions that are studied. There are lots of design tools that people are building, everything from new programming languages and logics and to like open source platforms for building these algorithms that satisfy these guarantees. And of course, developing lots of specific algorithms for specific problems. Especially, there's a huge literature on deep learning and training large language models now, but also census summaries, analyzing networking data, clinical data, data from social networks, mobility data about how and where people move around. And there are connections to a bunch of different areas within computer science. Obviously, maybe algorithms and security are obvious. Statistics and learning should also be clear, but also maybe less obviously connections to game theory and economics, databases, and these sort of programming language tools that go in. New tools are required to adapt what we know about formal methods for thinking about differential privacy, for example. And increasingly, as I said, it's sort of there's this interplay with questions in law and regulation and public policy. And of course, Waterloo is lucky to have at least one person who's contributing to many different aspects of this program. Okay, so that sort of concludes the second part of the talk, and I intentionally left myself, a variable amount of time for the third part of the talk. So Gautam tells me I have till past. I promise I won't torture you that long. But if people have to run out because they've got other classes or whatever, I'll understand. And I'm happy to take questions at any part of the talk. Yes. Yes, absolutely. Sorry. Yeah. Yeah. Yeah.
First, in practice, how people manage running out of budget in Google or other places? How do they manage it?
It's a great question. So the question, just for people on Zoom, the question was, how do people manage running out of this sort of budget of epsilon? So I've described epsilon as a leakage measure, but it's often productive to think of it as a budget. And that's because when you run multiple differentially private algorithms, this epsilon quantity adds up across, and I mean, you can upper bound how quickly it increases as you run more and more of these algorithms. And so it's often useful and like fairly accurate to think of it as a budget on how much you can leak about your data. And the question is, what do you do when you run out of budget? So there are various answers to this question. In some systems, the answer is you reset the budget to 0 and start again, which is not a great answer, but it is indeed what many systems do. And the mentality there is that what you're doing is you're sort of providing the protection not to like all of one person's data, but to like the behavior, a person's sort of contributions to the system during a given time window, for example. Maybe a more principled way to approach it, which is like what they're doing, for example, at the Census Bureau, is they sort of do a fair amount of planning at the beginning to think what are the things that are going to be the most broadly useful places to spend budget, and they do things like case, focus groups, and they actually sit down with the, sociologists and demographers and whoever needs to use the data to see what they need. and then they reserve a part of the budget for future needs, so that they give themselves like a backdoor if they need one to sort of change, to release more detailed information in the future. And the other component that people do is sort of to distinguish different types of access to the data. So one solution often is to create like sort of a privileged access programs where people who are vetted appropriately basically get their own personal budget that they can use to just do their own analyses. And so if in principle, if all those people colluded and shared information with each other, then you would blow your budget completely. But on the assumption that people are somewhat principled about sharing that information with each other, then you get some meaningful guarantees. And if all of these sound like sort of not entirely satisfactory ways of getting around this problem, that would be an accurate impression. Like it is a real issue with this type of it's a real issue, and it's like it's something we understand is at some level fundamental. Like you just cannot release everything everyone would want to know, and so you have to choose. Whether or not the frameworks we have for choosing are optimal, that is like less clear and probably not. But I think it's, broadly speaking, a work in progress to figure out the best way to do that. Yeah.
I have a question regarding the memorization.
Mm-hmm.
So you choose a subset if that subset is different for every instance?
Yes.
Is the S related to the marginal distribution? That's
let me go back here. Sorry. This is going to be the best way to do it. No, sorry. One more try. Okay, I'll fix this in a second, but here. Here's the slide from earlier. So what is actually, you know what? It might be beneficial to go kind of look at some examples. I didn't present this slide, but this is sort of a backup slide I have. So in the examples we come up with, the data come from, as I said, they come from distinct subpopulations that you can think of as sort of geometric like clusters in the space of data records. And my job as a learning algorithm is to figure out which subpopulation a record came from. And the set S these are the examples that are somehow single representatives of their cluster in the data set. So which part of the data set forms that special set S will be different from sample to sample, because it's a random quantity.
And is it different for different marginal distribution? Is there a problem? So okay, is it different for every different marginal distribution? I'm just curious how the marginal distribution affects the choice of these clusters.
I'm not sure what you mean by marginal distribution. Do you mean on the coordinates of X or?
No, the instances themselves.
Like the P in the distribution.
Right. Oh, yeah. So it is. Yes. So which set these are will depend on P, and P is not known. So P is itself actually, the way we set it up, P is itself a random quantity, but it's like not known to the learning algorithm what population it's dealing with. It knows like a family of populations, but not which population it's dealing with. And so how we assign membership in S depends on P implicitly. Yeah. I'm not sure if that totally answers your question. Okay. Yeah. Good. Yeah, we're at, yeah, questions. Questions are good. Yeah. Indeed. Let's try that. Yeah.
So I had a question about the choice of how you measure the closeness of the distribution.
Yeah.
So, I mean, so this is saying that the probability the output is in S is like 1 plus minus epsilon of for any between two neighbors. Like if I instead define it as like the total variation distance between the output distributions is small. The smallest diameter by some epsilon again. Would that I mean, is that more natural or is it like N is not that?
Yeah. So let me see if I can give you a couple of answers. I'll give you like three answers to the question. So question number one, answer number one is people do consider a variety of other divergence measures on probability distributions. Many of which have this flavor but change a little bit. Like there are these various Renyi divergences, for example, if you know that, sounds like you might know what that word means. And many of them have a similar interpretation. So the sort of second point is the reason this multiplicative measure works really nicely is that it actually allows us to kind of make conclusions like this when formal. And it's because this is a divergence measure that plays well with the construction of with Bayes' rule, if you will, like with the construction of posterior distributions. Total variation specifically doesn't work well, and I'll give you an example. So for example, one thing I could do if I sort of, let's say I hypothetically ask the same set of questions to each of the 350 million or so people who live in the United States. And now what I'll do is I'll just pick 10,000 of those people uniformly at random and publish their data in the clear. Okay. Names, you name it, it's all there, right? So what definition does this satisfy? Well, it turns out this satisfies like a total variation distance style guarantee because the probability that my data wind up in this sort of public sample is fairly small, in this case on the order of, 1 in a few thousand. And the problem is that if you kind of tune the parameters so that the probability of me winding up in the output is actually small, is like the probability that any bad thing happens to anybody is small, then you wind up not being able to do anything useful under that definition. So total variation distance, it turns out, is like the wrong handle for this particular, by which to kind of grab this particular problem. The other divergence measures I mentioned, they are useful, and they're often used as intermediate steps in the analysis of more complicated algorithms for reasons I could like explain on the board, but aren't maybe salient right now. Yeah, that. Okay, I'm gonna take a little bit of time to talk about this third part of the talk. I realize, people may be running out of steam. So if you need to grab a cup of coffee, but feel free to, like I said, step out. I'll be brief here. It's already 10 past. So just a quick reminder on Gaussian distributions and multivariate Gaussians in particular. So these are a, basic distribution on real valued vectors in high dimensional space. They are characterized by sort of two high dimensional quantities. In d dimensions, you've got the mean of the distribution, which is a d-dimensional vector, and then the covariance matrix of the distribution, which sort of specifies, the mean specifies like what the data is centered around, and the covariance specifies the shape of the level sets. So the level sets are always like ellipsoids, but which way they're oriented and how big they are, that's what the covariance matrix tells you. It also tells you the individual correlations among any given pair of attributes in the data set. So I'm sure you've all seen this at some level. I just want us to all have like be on the same page to follow what comes next. So like just things that are useful to know about this is that, when you draw samples from this distribution, they all tend to lie in this sort of density plot picture, they all lie in roughly the same place in high dimensions. They sort of line up along the boundary of some typical level set of this distribution, what I'll call the typical ellipse. It's not a standard term. I'm just using it for this talk. And also, we can estimate mu and sigma using fairly simple formulas. So the best way to estimate the mean, it turns out, is just to take the average, the empirical mean of your data. And then it turns out a good way to estimate the covariance matrix is to take the matrix of empirical correlations or covariances between coordinates of the data of your data. And so this is written in matrix notation, but it's basically the average of some little matrix you construct for each example. Okay, so what's our problem? Our problem now. So this is this is a well understood problem. We've been studying this since Gauss. So our goal is to construct a differentially private algorithm to solve this problem, so that for all mu and sigma, if you give this algorithm examples drawn IID from normal mu sigma, then it will produce an approximation to mu. And exactly what notion of approximation is important here. So again, here's my distribution. Here's my typical ellipse. What I want is, I should mention, sorry, this private Gaussian mean estimation, it's like an interesting statistical problem unto its own, but it's also a basic step in a lot of machine learning inference algorithms. And maybe one question is, like, what do we mean by approximating this well? Well, we want, so this is following, this formulation in the setting of privacy came up in a paper actually of Gautam's. We want the error of our algorithm to sort of track the natural structure of the data. So if there are, in directions where the data has very little variance, we want to have very little error. In the direction data has more variance, we're okay with more error. And so we'll sort of measure error in some rescaled version of space where we've rescaled things by the covariance matrix, or its square root, rather. And so this is sort of like saying what we want is we want our estimate to lie in some like scaled down version of this typical ellipse. Now, if privacy were not a constraint, we would just publish the empirical mean of our data. And the kind of guarantee we would get out of it is that this special metric that I've defined here would, for all mu and sigma, this special metric would be very close to square root of d over n. Okay, and so basically once I have enough data samples, I get a small error even in this kind of rescaled metric. And so what we want is some sort of analog to that statement. And this is something that, as I said, was sort of first really studied explicitly by Kamat, Lee, Singal, and Ullman, and there have been recent results on. So the kind of pair results I wanted to tell you about was in a couple of papers with my student, Gavin Brown, who's now a postdoc at Washington. And roughly speaking, what we show is that there's a differentially private algorithm that has error that kind of competes with the best thing you could do non-privately, plus some additional term. And this additional term, it turns out, is basically like due to the privacy constraint and is basically can't be improved any further. So neither of these terms can be significantly improved. And the thing maybe you want to notice about both of them is they both start getting small once the number of samples exceeds the dimension of the system. And so we could do this sort of with no a priori assumptions on where the data lives. So we don't need any a priori assumptions on either the mean mu or the covariance sigma. And this sounds like a weird thing to be excited about, but one of the cool things about this result, I can't tell you. Thank you very much.